Let's continue with the fourth section of this abstract class field theory, abstract valuation theory, the fourth section. The further development will now be based on a fixed choice of a surjective continuous homomorphism from a group profinite group G to the completion of Z. And this is a surjective map. So this is given. We fix it at the beginning. This homomorphism will produce a theory which is an abstract reflection of the ramification theory of p-adic number fields for local fields. Indeed, in the case where G is the absolute Galois group of a p-adic number field K, such a surjective homomorphism arises with the maximal ramified extension in the following way. So let's notice the notation. Maximal ramified extension he used, I think here is tilde. It's not K-bar, it's tilde. Because for K-bar usually we use it for separable closure or algebraic closure. Yes. So here is, you see this is K-bar. This is absolute Galois group. But here is tilde, okay? This is the maximal ramified extension with this notation. Okay, so here is giving the motivation, okay? These are the motivation. This is a concrete example. We understand, nothing very abstract nonsense. This is the concrete case. If FQ is the residue class field of small k. Let's do it this way. Small k. Its residue field is FQ. We already saw that we have this isomorphism of absolute Galois group. Actually, we saw that this is the projective limit of and this is because it's isomorphic to G. This map is mapping the Frobenius. And I can prove this is small. This is what we saw. And taking the injective limit, we got this. Which associated to the identity element of Frobenius automorphism. This is defined by it. Frobenius is defined by origin to the qth power. So this Frobenius. This notation is the same as that's it. This is true. The maximal ramified extension. Unramified extension is residue field. Its Galois group is always equivalent to the. Its Galois group is the same as the Galois group of its residue field. That's it. Okay, that's a theory we know, but there's something local field theory. The forbiddance is the reason to the Q spavel. It is only when you quotient by the local field is characteristic Q. You can do this. This is a morphism. If it is not characteristic Q, it's not a group homomorphism. It is into Q spavel because you have to be homomorph. You have to make sure that you have this right. Weirdest notation. O, respectively. I'm sorry, it's P or Q? P or P. Do you know the valuation ring of this maximal ramified field? Respectively, it's maximal ideal, and the valuation ring, the OK, the M, you need to know, okay? The homomorphism. In question is then given in this concrete case as the composite. Here it is for this very concrete case example, how to construct this assumed D at the beginning for the abstract case. In this very case, what is this? G is the Galois group of K bar over K. So we map it to K2 over K because what? Because this is a Galois extension. Because K2 over K is a Galois extension, so we do the quotient. This is a quotient map. This map become normal. This is a normal subgroup of G. So by the quotient of the restriction map, we come there and we have the isomorphism. So we constructed this D. Precisely, this becomes the motivation for the abstract case when we are not very clear what is the G. G is just profinite group later. It's not a known field extension. It's not the Galois group of a known. It's not the absolute Galois group of a known field extension of a known field K. Although we know that for any profinite group, it is isomorphic to the absolute Galois group of some base field K, but abstractly we're not doing that way. I think we will see. Anyway, we have this concrete example. In the abstract situation, the initial choice of a surjective homomorphism mimics the p-adic case, but the applications of the theory are by no means confined to p-adic number theory. The kernel I of D has a certain fixed field. That is the kernel. Okay, that's the quotient. This is the kernel. Has a certain fixed field, that's it. And D induces isomorphism. Exactly. More generally, for any field big K, we denote by IK the kernel of the restriction. More generally, for any field big K, we denote by IK the kernel of the restriction. And call it the inertial group over big K. To understand this notation, GK, what is GK? GK by notation means the Galois group. It means Galois group of K bar over big K. And what's the relation of GK and G? It is contained a subgroup of G. When you have to fix less, you are bigger. When you have to fix more, you are smaller. Okay, this is subgroup. So actually we don't know whether this is surjective, but we know the kernel is the intersection. The kernel of this map. So this map is GK contained in J, then through D map it to the hat. We denote this kernel by IK, but surely this will be the kernel of Y intersect with GK. And we know what is I. I is exactly this one. This is this one, and it is I. And we know for intersection of Galois group, it corresponds to the composite of field, the fixing field. We denote this the fixing field of IK, and we call K2 over K the maximum ramified extension of K. Okay, let's do some recalling. This is small k, and we have the maximum ramified extension for small k. It's inside K bar, and here we have big K, and for big K we have maximum ramified extension. Okay. And of course it is contained in small K bar also. Put it here. Okay. Now what we do, we are going to define something similar as what we have for local field, something like ramification degree and inertial degree, defined to be the dimension. So this is the dimension for the image of D inside the Z hat. And the ramification degree is the dimension of Number 10, when Fk is finite, the surjective homomorphy. And this is finite. It means your image is just finite index subgroup of GK. Of course, you can by giving more denominator to make this surjective. Okay? This is easy. With kernel IK. And have isomorphism like this. Of course, we know that UK quotient by IK is with this, so we have an isomorphism. But why this kernel is IK? For D, I know the isomorphism is IK. Okay, sorry. This is dk because this is not D. Sorry. It means that if D is not we already know that D is surjective, but we do not know whether this is surjective. But he says that if Fk is finite, that this one is also surjective. Fk is defined to be the way that to make sure that dk equals D equals Fk, because D is surjective. So in this case, this is dimension of K. Sorry, of course this is equal by definition because it's surjective, and here is this is the definition of dk. Actually, it's not the relation we find, it's a definition of dk. Before this there is no dk. Okay, we define dk to be 1 over fk of d, and we denote the kernel by ik. We denote the kernel by ik. Actually, it's not we denote the kernel by ik. Ik is already defined. Ik is the kernel of D. And so, it is also the kernel of dk. Why? Because it's obvious. They have the same kernel, okay? Because if this is maps something to 0, then D maps it to 0, so it's just a coefficient. Actually, it's a good question why this is isomorphism, because we don't know. There's no evidence this is surjective. Gk to z. What we know is only g to z hat is surjective, but gk is just this. It can be any subgroup if you want. But why is isomer? Why is surjective? It's still assumption. We only consider those k making this surjective, okay? And so we have isomorphism. When we discuss something on this topic, we are only interested in those GK that has surjective mapping onto the hat. Okay. Definition: the element phi k such that decay phi k equals 1 is called the Frobenius over k. That's the definition of Frobenius element. It is those mapped to 1. For field extension over K, we define the inertial degree and the ramification degree as follows. Okay, that is nice. And we will say we have this relation. It's just by group theory. Proposition: for every extension over K, we have the fundamental identity. L K dimension inertial times ramification degree. Proof. The exact commutative diagram immediately use if L over K is Galois. The exact sequence. What is this? Yes, we have this. We have the commutative diagram. Yes. This by assumption. We always assume this is surjective. Assumption. This is by definition of kernel. Okay. Definition of IL and IK. This is a kernel. This diagram commute. Why is commute? It's just inclusion. Nothing. Okay. Immediately use if L over K is Galois. The exact sequence as following. Do the quotient. Yes, this is by if you want sneak lemma. Okay. If L over K is not Galois, we pass to a Galois extension. Continue L and get the result from the Bauer transitivity rules for E and F. This has degree E. This has degree F. This is quotient, okay? This is just by fundamental theorem of group theory. Alpha is called unramified if the ramification degree is 1. Consistent with the notation for local fields, okay? Value is contained in key L into key 12. Alpha is called totally ramified. Okay, this is true if and only if this is contained in key 12 because this is a maximal ramified extension. And alpha is called totally ramified if the inertial degree is 1. And this is if and only if intersect with key 12 is K. Because what this is to say Q12 is K. There's no unramified extension. No, this is not Q12 anyway. What we want to say is that in between this should be unramified. But this is trivial, it means that there is no unramified. In the unramified case, we have the surjective homomorphism. This is the quotient. When you have this, you can do the quotient. And why these are normal, why these are Galois extension? Maybe we are just considering Galois extension. We're only considering Galois extension. Not this part. This is not obvious. I think we need the condition that L over K is Galois. Otherwise, how do you calculate the quotient? Anyway, we put this question here, maybe. It's not very clear for me. Okay, if Fk has finite index, we call the image Frobenius automorphism. recall that. What is phi k? Phi k is an element of G key tilde. No, sorry. Key tilde over k. That is mapped to 1. Phi k is here. And the image, we call it the L over k. The Frobenius automorphism of L over k. For arbitrary extension over k one has just become the composite. See? L tilde is the composite for L and k tilde. Why? Because this should be this by definition of k tilde. And then the LK is L, so this is LK tilde. In other words, they're both yes, and we have L tilde. This is the definition for L tilde, okay? And this is the maximum ramifier subextension of L, okay? Clearly has the degree. If you want, you can do a little computation why this is a maximum ramified extension. It's because of the initial degree. Because this is unramified. And this is maximum ramified. In K bar it should be. It should contain L also, of course. So for the unramified part of L over K, it is actually contained in this part. So it's this one, okay? This is degree. And then we have the proposition. For two field for field extension over K. Fine. Okay. Sorry, we come back to decay. When we denote decay by 1 over fk over d, we see that y is surjective because we assume maybe not. We do not do it in this way. We only know that we assume d is surjective. Okay, and this is when we assume fk is finite. In this case, if it's not surjective, we should know that it should be of the form. It should be of this form for some z, the image. So we quotient by the over fk, it becomes surjective. And it is because of this we can define this. Otherwise, both of them are surjective, then this is 1, but it's not. It's both of them are contained in Z hat. And here, that's why we can write, we reasonably write this. Okay, this is the image inside it, the image of GK inside it, and the difference by a finite number, which is initial degree, so it commutes. We have this. And for Frobenius GL, as we call GL, it should be an element over here. Now we restrict to Kia. We restrict to Kia. This is inside. We restrict to Kia. What is this? This is restriction. What is restriction? Restriction. Do the quotient. How do you do the quotient? The quotient by you quotient by the subgroup L bar over K bar. So this is inside the quotient. If I K is already there, what is this index? This index is because of what? Because phi L, it's raising to a different power and phi K. Of course, this is some proof, but from here we should know why. Say why for Frobenius we have this power. It's because the inertial degree is important for Frobenius, because Frobenius is raising to the power of the chapter of the residue field, isn't it? Back to the definition of phi k, we say it is the element of this group whose image is 1, which means that if we look at the L, it is related with this this inertial degree actually. You understand? For example, if I write here the L, and as we say, this is quotient by quotient restriction map. We do the restriction map. You see that which means that phi L, this is mapped to 1, and here so phi L restricted to K will map to this, not map to 1. So shouldn't it's telling us that isn't it telling us this? Because phi k is mapped to 1. Yes, the problem is here. You have to recall this map is not multiplication. It's not if you recall this, how is this group defined? How is this isomorph? Mapping the Frobenius to 1. You're right, but it's by what? By the multiplicative. It is by this isomorphism. It is sigma to the power n that is mapped to m here. So here, if this is mapped to f over k, you should do the f over k is mapped to the 1. So we have this. Okay, nice. The Frobenius automorphism governs the entire class field theory. Frobenius automorphism. Okay. It is a generator. It is a generator. It is important. It is a generator of the Galois group. It's the topological generator of the profinite group. It is it is important. Like a king. It is therefore most remarkable that in the case of a finite Galois extension of OK every sigma in the Galois group of over K becomes a Frobenius automorphism once it is maneuvered into the right position. This is achieved in the following manner. For what follows, let us assume systematically that Fk is finite. We pass from the Galois extension over K to the extension L12 over K and consider in the Galois group the semi-group. So this is a semi-group and consists of elements subset, as I said, is subset of this group with integer image under decay. What is decay? This is decay. It's isomorphic. One over Fk times d. Observe here that decay factorized through this because what? By quotient GR. Actually, the problem is whether we have this. So we have to look at the kernel of this map, which is GR prime. It is containing the kernel of this decay. So it's factorized. For finite Galois extension, here is Galois extension. The mapping is surjective. This is important proposition, and it takes time to prove. But you say for Galois extension over K, to have a surjective image, or let's say to cover this if you want. You have to use the maximum ramified extension. Look at this for minutes. This is enough to cover it. Of course, as a subset, this is a subset of G. I'm not going to the proof. This is not very difficult proof. As every element may be lifted to an element sigma, and this group can be lifted to an element in this Frobenius. How do we call this? Didn't give it a name yet. The following proposition shows that this lifting considered over its fixed field is actually the Frobenius automorphism. This lifting is the Frobenius automorphism considered over its fixed field. Fixed field of this element. Now we find this element is very nice regarding to this fixing field. That means you look at this. Look at this field, it's very nice. Maybe not this one. It's always here. Motion, I think smoky big key, yes. This field is key. Fixing field. So this is a very nice element for this group because it will be the Frobenius automorphism of this group, which by definition means the pre-major one for the isomorphism. For the isomorphism of so it means this element will be mapped to 1 under this sigma. Decay of this group, decay of this element, sorry. This element will be the Frobenius of this. Yes, that's exactly as what we said. It has illustrated the situation described in the last proposition by a diagram, which one should keep in mind for the sequel. So it is here. Nice. All the preceding discussion rows entirely from the initial data of the homomorphism. We now add to the data multiplicative G module A, which we equip with the homomorphism of this to play the role of a Henson evaluation. A Henson evaluation of AK with respect to, so by the notation we recall, AK is A fixing by GK. This is AK. A fixed point of view. And we define homomorphism from it to Z hat. This is always related to a fixed D. But what is GK? GK is again for the subgroup G, and for the provided group G, there are many subgroups and whose symbol give fields. We call the fixing field of this group symbolically. And then we have GK. And we are now going to define an Henson evaluation for AK. If we satisfy the two properties, the image of AK under this evaluation have to contain a ring of integer. Have to contain the integers up to after modulo by n is this. The valuation of the norm of AK. Have to be the image of AK multiplying by FK in the coefficient. Exactly like the original homomorphism, the Henson evaluation has the property of reproducing itself over every finite extension, big K or small k. Reproducing itself over every finite extension. How to reproduce it? In the following way. For every field K, which is finite over small k, so what is small k? I think he means this. For some small k. This is finite things. Quand il est fini, for every field big K, which is a finite over small k, the formula defines a surjective homomorphism satisfying the following property. For every field big K, which is finite over small. The formula defines a surjective homomorphism satisfying the following properties. What is V? V is the Hamiltonian valuation just defined. So, is there a big key and a small key? Right, this is big key. Different big key and small key. This is small key. Small key. Small key. Big key and small key. And you do this. I'm always a little confusing about the norm. I'm lacking the intuition that norm is making something higher into something lower. In what sense? It's know that for some element from a real integer of a higher extension, we apply the norm and it becomes the element of the lower real integer of the lower extension, because it's ending the symmetry of this element, because you apply all the Galois action on this element, and finally you say that after doing this norm, then it is invariant under this Galois group, so it's in the fixing field, and so it's falling into the lower field extension. This sounds very naturally nice, but for me, I'm still lacking intuition, but it works. Okay, nice. So we write this, we know if some thing is in the level of k, and we expect after applying this, it becomes some element in the level of small k. Once you are in the level of small k, I can apply v. Okay, something like this, and I have to say, when we do this, what's the relation with vk? It's different by a coefficient. That's what proposition is telling us. And the failed commutative diagram as following. Okay, describing the relation between two Hamiltonian 2 Henseling valuation. A prime element of AK is an element that has only valuation 1, and we put those at valuation 0 UK. This is like the units of real integer. Okay, AK is like a real integer in the form, but it might not be, because we know sometimes it is finally like for field. It's the multiplicative field. It's the multiplication group of the field sometimes. Okay, anyway, a prime element is defined this way for unramified extension, that is the extension such that this definition of unramified extension we have from 4.7, that they have the same valuation. It sounds very nice because it's unramified. Same valuation is reasonable. In particular, prime element of AK is itself also prime element of AL, because they have the same valuation map, hence the valuation morphism. If on the other hand our AK is totally ramified, if on the other hand our K is totally ramified, identical if our K is 1, and if pi L is a prime element of the AL, if pi L is a prime element of AL, then pi K is a prime element of AK. Then this prime element of L and over K are not the same, and the relation is like this. You see again an element of L after you applying the norm becomes an element of K in the level. That is handing you some coefficient depending on the cardinality of L or K. Because in this case, right, it should be the cardinality, but yeah, because what I mean is, if you take element of K, it will become, right, first is linearizing from K. I think we stop here for this section.